in verification, making your engineers smarter. Big data is getting a lot of press these days, but does it really apply to ASIC verification efforts? HPE has found that it does apply and it can be instrumental in helping make smarter decisions. HPE is taking small steps to capitalize on a concept of big data. In this paper, we will share our view of using the big data concept in ASIC verification domain, highlighting several specific examples of how is it easy for the audience to get started with their own big data analysis. We will also share our ideas on where we see larger big data opportunity being able to help our verification effort in the future. Introduction. Big data is commonly used to term across the industry that is defined by the volume, velocity, and variety of the data collected. However, does everyone really understand how to get the value from it of verification? In this paper, we apply big data technique in verification and show that it is not a scary topic, but rather than one can be significantly helpful in the reader. We have come to realize that big data isn't just about its size, but about the ongoing impact it can have. We need to get our product to market sooner to meet customer needs faster than we are doing today. To accomplish this, we are using this data to drive more accurate forecasts for licenses, compute resources, engineering resources, schedules, and equip our verification engineers with the critical data to enable them to make smarter decisions for all current and future ASIC projects in our organization. We believe that identifying new data sources, correcting them continuously, and inventing ways to analyze them fits the definition of the big data and has helped us reach those goals. We show the gigabyte of the data can be analyzed without complicated, time-consuming custom toolsets and complex MapReduce operations stored in those secure databases and does not require artificial intelligence to make a conclusion about data. This makes big data analysis accessible to any design and verification team by using these techniques on data that can be easily collected and analyzed, no matter what its size. Our team has been collecting and analyzing data from our ASIC development efforts for years. From this experience, we present a practical and real example of how we are utilizing big data in our verification methodology to drive a smarter decision. For our role is to make sure that the people who need this data to make decisions to have the data. To do this, we first focus on how to identify and collecting the right data to answer the questions that need to be answered. This helps our team perform verification tasks smarter, not by changing how we write tests or test benches or checkers, but by helping us increase simulation throughput and performance, monitor DUT performance, bandwidth, and latency, and improve the test effectiveness through more advanced coverage analysis, enabling us to find bugs faster and reduce our time to market. Next, we show real examples of how we are presenting and analyzing the data that is collected. The data must be presented in effective ways that lead the user to answers they need. Practical examples will show how we look for anomalies in the data, how we use data to identify ways to address challenges, and how we move from simply having data to transforming into information to be acted on. To illustrate our use of big data, we focus on the following areas: compute farm metrics, performance data, and test result data, and big coverage data. For each area, we show the specific types of data we collect, how we store it, and how we analyze it. The practical questions that we need answered with this data are shared to demonstrate the value that big data brings to your team. 2. Collecting the right data. Collecting the right data makes all the difference in the types of questions that can be asked and answered to enable verification engineers to be smarter and more efficient. The data in Table 1 has been invaluable in helping us to ask and answer these questions and drive smarter decisions. The Table 1 types of data collected: compute farm metric, performance data, test result data, and big coverage data. 3. Compute farm data. The compute farm data we collect outlined in Table 1 captures information every 6 minutes per user, site, business, and give us the tremendous insight on the state of our compute farm jobs. Detailed license usage data from our license servers, information about our fair share license request queuing from our job manager, compute host loads, and disk usage metrics. This data help us to answer various questions about our licensing forecast, license utilization, and compute farm queuing issues, and enabling us to make a smarter decision about the purchase and manage these resources more effectively. The types of the questions we have answered with this data and the corresponding case study follows. A. Asking the right questions. Knowing what the actual versus expected demand of licenses lets us ask a question like, what do my job submission pending time seem unusually high study? What is causing this? Why are all my user jobs being starved for licenses when they are supposed to have the highest priority? Why did only half of my test run over the weekend? Why did one team scan more than their fair share of the license allocation in regulations last night? How much disk space and memory will we need in the future? Some user jobs are starving regressions. Exactly which users are they and what are they running? Answer to these questions help us understand actual demand versus expected demand. We can tell users things like you're running 24 times 7 with the 20 licenses. You are running 24/7 with only 15 licenses. We can spread the licenses out across our teams to get better utilization. When you are out of licenses, you typically spend more money to get additional licenses because you don't have the data to tell what is really going on. And knowing the license utilization lets us better allocate and use our licenses. We can see the big data with the organization and the site to have been using in the licenses. We can pinpoint where the problems are coming from and adjust their utilization appropriately. B. Case study. Why are my user jobs being starved for licenses? We had a situation where tests were being starved for licenses. It starts with a simple question: why was our demand for licenses so high, causing user jobs to be starved for licenses during the day? We pulled up the pending jobs chart from our web interface, see figure 1. We saw the demand sparking, causing user jobs to be served for licenses. Our compute job farm metric database showed a window of time where the problem occurred. This was a transient event. Users felt like it was taking longer for their jobs to run, but without the data, we wouldn't have known if it was a real issue or not. Even if we believed it was real without the data, how do you track down the transient event like this? By the time you investigate, the issues has cleared up, but your engineers continue to be impacted. After analyzing our available license count against our pending user jobs, we discovered we were being starved. See figure 2. Our regression jobs are required to obey a buffer limit which assure licenses are always available for users. They can take licenses reservations for user jobs, yet our license availability was clearly falling below this buffer limit. So, who was taking the licenses? Available licenses fell below our buffer limit and license availability, causing response time for user jobs to increase. Figure 1, compute job data, depending job spike. Figure 2, compute farm data, available licenses below buffer. We looked at our licenses server approach, organized by business, to find out where the licenses were going. See figure 3. We found another business was getting more licenses than we were. We also discovered the same business was also using more licenses resources that they were supposed to. See figure 4. We now knew which business was taking the licenses and preventing our jobs from running, but we didn't know why. We asked some additional questions like, who made the license count jump? Who is running jobs in the business? We started looking at their jobs for anomalies to point to what they were doing incorrectly. Were they specifying the license limits properly? Were they asking for and reserving the license resources they were using? We used live data to know which users were requesting resources, showed them the problem, and had them correct their resource request, which ultimately solved this issue we were having. Figure 3, compute farm data, business license usage. Figure 4, compute farm data, business resources usage. We also found a second repetitive issue you can see in figure 1. Each day at certain times, a spike similar to the original one was found. One problem being solved led us to solve these secondary problems too. What are these license demands? Where were they coming from? We found that our continuous integration jobs were set to start at the same time during the day across all our projects, causing spike in license demand. We were able to flatten that demand by spreading these jobs throughout the day. Big data helped us to ask these questions, and the plot helped us answer them. This enabled our engineers to get back to the work quickly, increased our job throughput, decreased our usual job pending times, and raised productivity across the business. Case study. Why aren't we using all of our licenses? Our regulation weren't running enough tests, so our first thought was that we needed more licenses. After reviewing our license utilization over the past several months, we found that we were never using 100% of our licenses. While the job manager showed that they regularly used all but a few of our licenses. We then looked at the various license states reported by job scheduler and found that a good chunk of our jobs were in a reserved license state, meaning the test has requested a license but hadn't actually used it yet. The two graphs in Figure 5 and 6 demonstrate this disparity. Figure 5 shows the state of all licenses seen by the scheduler. About 10th of all licenses at the same time were tied up in reserved green, and very few free licenses blue at many points. Figure 6 showed the license server reported only reached about 90% of license utilization. We decided to investigate these jobs in the reserved state and found multiple issues that resulted in better license usage. In this first issue, our simulation job flow is split into multiple parts: compilation, elaboration, simulation, and post-simulation script. Only some of these steps require license. In this case, we realized that our post-simulation script, which spent most of their time compressing and copying files and were causing the scheduler to reserve the license when none was needed. We revised the tools managing our jobs to return licenses after simulation portion had completed to open their license back up, leaving our post-simulation tools to complete without holding up other jobs. The second issue was whether the compilation step could be improved. The vendor tools requires a license for this step, but it was a lengthy process and that only needed a license for initial setup. We worked with the vendor and used our big data analytics to demonstrate the license bottleneck this imposed on us. The vendor made the appropriate changes so that the compilation didn't require a license the entire time, which freed up more of our jobs to acquire available license. The overall benefit here was better cycle throughput per simulation license without purchasing additional licenses. Figure 5 is the job scheduler license usage. Figure 6 is the vendor license usage. Next is the performance. 4 is the performance data. The performance data we collected outlined in Table 1 enable analysis of different aspects of our design performance while also providing insight to aid debugging performance issues. While we utilize the internally developed for the AutoPerf to obtain and to analyze this data, the approach AutoPerf is to instrument the design and uniquely identify the available measurement and present those measurements in tabular and graphical format. AutoPerform generates and records all requirements it can from the available data and lets us users to review the measurement they desire. AutoPerform uses unstructured data and aggregated corresponding measurement from multiple tests from the same testbench. The use of the unstructured data lets users create new analysis as needed instead of requiring significant effort in advance to plan to execute a new performance item and each data model. The software architect of the AutoPerf consists of the verification library, performance analysis tool, a vertical database of the test's performance result, and the web application. This data helps us answer various questions about the performance of our DUT over time, enabling us to catch performance problems as they happen. The types of questions we were answered with the data and corresponding case study follows. Asking the right questions. Measuring the performance and latency on each interface across each performance workload, configuration and test bench let you to ask questions like, am I hitting the performance metric we needed to hit? When did we stop hitting the performance metrics we needed to hit? What set of swept parameters across multiple tests gave me the best performance? Have we met our performance requirement for each specific traffic class? Answers to these questions help ensure that every test bench meets its expected performance target and help us to isolate when the design changes cause performance to drop. Our performance data helps us to spot anomalies on our design in real time as they happen. The case study. Why did our mover bandwidth take a sudden drop between this week and last week? Figure 7 show the input versus output bandwidth of the typical data mover operation with each data point coming from specific performance tests all run over a period of time. The ratio of input to our BW is related to the size of the transfer request. We would have expected to see a tight clustering of points for each transfer size around the expected bandwidth numbers. Instead, this plot showed that something changed the cause of our BW to fall off dramatically. We run, record, analyze, and plot data from our performance test runs in our nightly regulations. If the numbers fall out of expected ranges using various outliers detection methods, a failure is reported for verification engineers to look into. We leverage the power of the big data to automatically fail us when something goes wrong. We don't have to manually analyze our performance test result each day. We have a script and a process running on the data, and it will tell us when something goes wrong, has an anomaly in the data, like in this case. Figure 7, performance data case study, expected versus actual performing drop. We analyze data from the April 17th, and by looking back at the auto-generated plot from that day, we're surprised to see that our data transfer commands were being read at the beginning of the simulation as shown in Figure 8. In the real system, these would be spread out over the course of the transfer. This was a stimulus bug that we didn't catch the first time we set up these simulations, leading on a realistic data transfer simulation, unrealistic performance numbers. This is a performance test case expected of actual performance drop, and this is performance data case study issue identified, and the performance data case study issue fixed. We analyzed the data April 22nd by looking back at the auto-generated plots from the day, and so our data transfer commands were now being read throughout the entire simulation as expected, as shown in Figure 9. The performance figure line. The performance drop flagged our analysis toolkit, and an automated approach helped us to recognize we had a problem, show the effect of fixing it. There were really two bugs here. First, we didn't realize our performance were higher than expected initially. Second, we weren't spreading out our data transfer commands throughout the entire simulation, which is proper modeling of the real software behavior. Without this data and our automated performance analysis tools operating on the data, we would not have caught this or been able to see and debug it as quickly as we did. 4 is test result data. Our test result data, outlined in Table 1, captures information from every simulation user verification job that is executed. This data help us to answer various questions about our design and verification environment, enabling us to make smarter decisions related to it. The types of questions we have answered and corresponding case study follows. Asking the right questions, knowing how many simulation cycles we are running on each test bench, lets us ask a question like, are we properly balanced between each test bench? Are any test benches being starved for cycles? Are any using more than their fair share of the cycles? Answered and that these questions help us to ensure every test bench is being run with the expected priority and volume of tasks set by our project priorities. Knowing how effective our regression testing is lets us asking questions like, what are our pass and fail rates? How many tests are we running per night and per test? What is our time to first failure? What tests are finding the most bugs? What types of bugs are we finding? Functionally, assertion, checkers, verification, test bench issues, test errors, and etc. What are our bug open and close rates? We utilize pass or fail and rate and buzz or close rate curves help us how mature the duty is and how stable it is as we approach the end of our milestone. Knowing how bugs rate compare with the verification cycles and cycles over time lets us ask questions like, are we running the right testing in regression that can find bugs? How do bug find rates vary with the verification cycles and cycles over time? Are we done finding these bugs requiring fewer cycles to hit? Are we spending our time hunting for corner cases bugs now requiring many cycles to hit? How mature and stable is DOT? An answer to these questions help us predict our schedule with greater accuracy, enabling us to allocate resources more effectively. The knowing our test distribution lets us ask a question like, am I getting the right distribution of a test? Are any being starved or not running as often as they should be? Is each team receiving the necessary amount of simulation cycles? For these cycles, is each team getting the right distribution of tests to bring the greatest values from those run? With this big data analysis, we learned that we needed to restart our longer tests and test the failed in the last regression first. This gives our engineers feedback from those tests sooner and reducing the overall testing cycle time. Knowing if our test simulation performance is optimal or not enables us to ask a question, what factors are causing performance degradation in our simulations? Teams want to understand if they are getting the optimal performance from their simulation run. We found instances where our simulation performance was degrading over time. But citing simulation licenses are most effective resources we are consuming. So, improving the simulation performance, let us avoid our purchasing licenses by using ones we have more efficiently. Knowing our CPUs and memory uses let us know. Ask a question like, what CPU and memory configuration do we need to upgrade my farm? What CPU configuration would be optimal for our current workloads? Has the CPU utilization of our verification workload for remained higher or having deviation over time? What memory configures will be optimal for our current workloads? We found that data analyzes maximum and minimum and the average memory utilization, and we can make these determinations and purchase exactly what we need. Knowing how many license hours were used over the previous year, let us ask questions like, what should my license forecast be for the next year? How many license hours were used on a given project? How many licenses hours were used over all projects and teams? Based on this data, we increased the accuracy of our forecasts versus actual license needs. Okay, B, case study. Why are my tests running slow and taking longer than expected? We analyzed our test result and found our simulation was running six times longer than normal. See figure 10. Figure 10, test result, data case study, simulation metric, max duration, seconds by. We've analyzed all of our simulations metric plot for that same day and time to see if anything jumped out at us. We found that there was a direct correlation between the increased runtime and the number of garbage collections done during the impacted simulation. Our queries revealed an exact revision of a code that introduced a dramatic increase in number of the garbage collection. We found a change in our test bench that led to a dramatic increase in the amount of the memory required to run the simulation. Since we haven't increased the amount of memory requested by the test simulator was garbage collecting to reclaim enough memory to meet the required memory demand. This thrashing of the memory led to a 6 times slowdown in all of our simulation for this block. We optimized the test bench and increased the memory being requested by the test to the reduced number of garbage collection required, which fixed the problem as shown in Figure 11. Figure 11, test result data case study, garbage collection metrics, problem resolution. 6. Big coverage data. Applying the big data method to a functional coverage offers several advantages of the system value cover groups that engineers rely on. Our work in this area is incomplete, but ongoing and has the potential to make coverage data more useful. The typical cover groups just record whether a specific condition with a block has occurred, but with a sufficiently large database, several terabytes or more, it becomes more practical to record all value changes event for the interesting signals within a design, such as state registers, buses, enablers, and small store signals. If enough context is recorded to each value, change the complex coverage, questions can be more easily answered, covered, or work can be more interactive and flexible, and the quality of the tests and regression can be better measured. A. Asking the right questions. Examples of more complex coverage questions, those involve multiple blocks in a large design, or question about the frequency and duration or sequence of events. A Microsoft a microprocessor engineer might ask, are pipeline A's and B and C or stored at nearly at the same time? Is this a burst arbitration scheme fairly serving all requesters, or are you FIFO-X more than third over fourth, 3 over 4th full at a time when many cache misses have occurred in fast end cycles? With appropriate tools, the data for test can be visualized through the line chart that are similar to waveform. Engineers can compose coverage questions step by step, visualizing the result after each step. A first step might chart all the time periods when a FIFO is more than 3/4 full, and a second step might use those time periods to mask a chart of the rolling average of cache misses. This work can be done interactively. Compose new questions without needing to immediately run regression to see answer. Once a coverage question is composed, it can become a metric for choosing the best test to put in the regressions. For or eliminating the redundant from the regressions, metric can automatically measure the quality of the regression over time as design and test change. B. 4 major components. A big data approach to coverage can include 4 major components. 1. A fast database with several terabytes of storage. 2. A way to instrument verification testbench to log activity in the database. 3. A web application to explore, measure, and present the data. 4. A REST data service to give other tools, script, and web pages access to coverage metrics. To record data from simulation in the database, we need to instrument the verification test bench, and this process must be easy or engineers not take time to do it. To record simple value changes in small signals and registers, we create XML files that specify the module names and hierarchical paths to specific signal registers within those modules. A script reads the XML files and converts them into executable Verilog code that detects the value changes as the simulation learns and records them in a compact ASCII file. After the simulation completes, a different script reads the ASCII file and stores its data in the database. For events that are more complicated than value changes, such as CPU instruction issuing, we provide a small library of the instrumentation or subroutines, and engineers can call these subroutines from their benches. The subroutines can record metadata along with the required simulation time, value, and signal names to create the richer data. For instance, when an instruction issues, the metadata could include the OP code and the source destination register IDs. The simulation performance impact of the instrumentation varies with the number of instrumented signals and the activity vectors of those signals, and is similar to the impact of the enabling cover groups. The database tables let us record the full text of event in their ARMOR simulation. We can retrieve not just a hierarchical signal name and the simulation time, and it changes to a new value, but also metadata, test name, data of simulation, simulation command line, person who ran it, RTL version, and more. So much time can be recorded that a large database needs a strategy to avoid exceeding the available storage. In practice, not all simulations need to record data. A representative subset of null regression can record data by default, and a command line switch can turn on the recording for other simulation on demand. The recorded data have a configurable expression data. Since all text raises its loses its importance as the big design changes. The expired data is automatically removed. The database might contain the data derived from user-defined metric, that is, the average FIFO occupancy. That requires a few less storage than raw data it is derived from. Derived data can be given a longer expiration period than the raw data. This preserves the important information for a longer period while minimizing storage of the raw data. To benefit from the data, there must be a practical way to visualize and calculate results from it. Our approach is to web the design application lets engineers define functions that operate the data to create a chart for both raw data and functions. The goal is to the engineers to define a function to measure where a test performance is intended to purpose. A large set of the primitive functions are built into the application, and user-defined functions are built up from primitives and from other user-defined functions. Primitives provide arithmetic operations, add, subtraction, integrated, logical operation, and or greater than, and a time-based operation, time shifting length. Some primitive consumed waveforms and return new waveforms, like add or mask, while other consumed waveform and return a scalar value, like max or integrate. Like otherwise user-defined functions can return either waveform or scalar data. Waveforms are visualized line chart and let us see the activity in a test over the course of the simulation time. Scalar values are visualized with a bar chart, letting us to compare how test or groups of tests performs against the user-defined metrics. Bar chart that a group test by their configuration settings could answer the questions. What configuration settings are best at stretching features of the following point unit? Bar charting that a group tested by week could answer the question. As weeks pass by, are our regression getting better at the stretching the floating point unit? Yes. The user-defined function that engineers create a valuable metric for a standard understanding our simulation, and we want outside scripted tools to have access to those metrics. A REST data service can provide access, so they take a thread that knows the names of specific metrics and a test filter, and test filter selected which test to calculate the metric across can ask how the selected test perform against the metric and save the reply to ask the network. The watchdog process can use the service to check on the health and nightly regression and automatically email and alert if the metric shows an unusual change. Web page can use the service update the table's coverage information. Potentially adaptive testing algorithms could use the data and services to check the metric past simulations before deciding what test to run next. Though our work on big data coverage is not complete, we've seen some challenges that come from this approach. First, the ability to visualize coverage data is most useful if the chart can be generated interactively within a couple of minutes and preferable within a second. The web application must be written in a performance in mind. For example, if a particular intermediate calculation is used to new data every day and is worth to automatically pre-calculate and catch intermediate result in the database, so that when a higher level functions interactively, they can use the reached result to reduce calculation time. Second, to limit storage cover requirement, we must thoroughly choose what data to record and how long to keep it. Tools must make it easier to adjust the storage policy. The big data coverage can reduce the need for the traditional functional coverage, replacing many system Verilog cover point with the user-defined metric that are more powerful and flexible. However, it's unlikely to replace corner case cover point that are highly unpredictability. This is because we don't want to instrument 100% of our simulations of volume in our database. The traditional functional coverage is a more efficient tool for those cover points. 7. Big Data Toolkit. While tools exist in the industry to help manage big data in verification, we've created our Big Data Toolkit mostly comprise open source to the few commonly available commercial tools. We've created a scripted follow around these tools to collect, analyze of the presented data, and guide our decision. We've analyzed we used these tools across different tasks in Table 2. Big Data Toolkits: collect, analyze, present. Structured DB, unstructured DB, data queries tools, and a present web framing framework, and floating and texture. The typical tool to maximize your ROI with minimal effort to using the big data toolkits above involved in defining a database schema, collecting the data, inserting data into a database, and presenting data for analysis. To accomplish this, you would first design the schemas around the data you want to capture in MySQL workbenches in or an object relational mapping ORM toolkit like DBIX or SQL Alchemy. Use then the right script, Perl or Python, and extract the data you need, either from the log files recording the Jenkins job at the same time data or other data sources, and insert that into a database schema. Next, you would write a query script in Perl or Python that could provide a rich command line interface to users query database with ease. You would also ensure the script can return the query data in the ASCII table, CSV, or JSON format. You'd then set up a web server using a custom web framework that uses a protein engine like ChartJS and Grafana, and design the set of approach you want to see. ChartJS parses data from your query script, and Grafana parses data directly from your data, avoiding the need to create a query script. These tools produce interactive charts that can be customized by the user to see the data they want, and they can export it to an Excel for further analysis. We found that this tool flow can be created by a small team with few resources in about our engineers' month of effort, and maintained by a few engineers' hours a month. 8. Future use cases. Although we are using the big data to answer these types of questions every day in our development activities, there is even more we want to do. In order to stimulate thought for the readers, we will briefly share some opportunities we will explore in the future. Coverage data is often stored by the EDA vendors in structured database and heavily summarized. As working with the EDA vendors to store this data, highly performing unstructured data using big coverage data items above would help us answer more questions about our testbench reaching a deeper and stage basis within our designs. We would like to see the improvement in intelligence test grading. Our test result data is currently stored in the structured MySQL database. We would like to store its unstructured data and use Hadoop to analyze it. This would enable us to store more dynamic and varied information per test. Engineers would have to decide what the test attribute, test mode, test bench, configuration, error signature, regression duration, and continuation, failing modes, register programming, coverage point they want to store, put data, test and analyzed, and when they need it most, while debugging, failing, closing, coverage, and etc. Additionally, we would like to expand our use of the big data to get a more even value from our cycles. Big data can help our team drive improvement in intelligent stimulus generation and coverage-driven stimulus. From analysis standpoint, we see the exploited opportunity in stimulus generation into leverage modern artificial intelligence and machine learning techniques. For data visualization, we will be exploring improvements such as pit map to summarize and visualize data and abnormally, and that to date, we have been analyzing the data with the domain within which the data was generated. There are additional opportunities to take a bigger picture view by querying and merging the big data across the multiple data domains. Data is often segregated into multiple databases, and performing queries across the database will let us gain even more insight. Yeah. Conclusion. While even more can be done with big data was discussed here, we've shown how anyone can quickly jump into the world of big data, leveraging the concept in their environment to bring value to their team. We have shown how asking the right question about the data you collect can read the insight that make your engineers smarter, letting them overcome the design and verification challenges. With big data toolkits, mostly comprised of the open source and freely available tools, readers can create their own big data infrastructure using databases for storage and query libraries for analysis and web frameworks for presentation and analysis. What questions can you ask to make your verification more intelligent? What data can you start collecting today to answer those questions? Now is the time to correct and go beyond simply answering the question with big data. Now is the time to enable the data-driven actions to change and improve your design verification ability. Thank you.